We're going to talk about kernel programming now. Has anyone ever done any kernel programming or like any sort of like lower level device drivery, hardware stuff? Cool. Couple of people. It's a really interesting world. Like I write a lot of Go code and Python, and delving down into the kernel programming world was totally different. And it's really fun. So now that we have some idea about what the kernel does and we know how to build a kernel, let's take a brief look at its physical organization. So there are two main categories of kernels, the monolithic kernels and microkernels. The Linux kernel is a monolithic kernel. And all this means is that all of the components that make up the kernel, the file system, device drivers, etc., all run together in the same address space. At the same time, the Linux kernel has a modular design. At boot time, only a minimal kernel is loaded into memory, and after that, whenever a user requests a feature that is not present in the minimal kernel, a kernel module is dynamically loaded. And that ties back again to what we were talking about with the Thunderbolt drivers. So conversely, microkernels have a much smaller code base, and they only load the bare minimum of services in kernel space, like process scheduling and memory management. And everything else runs under something called user space. So what is kernel space versus user space? Modern CPUs operate in two distinct modes. Kernel mode. In kernel mode, the executing code has complete and unrestricted access to the underlying hardware. It can execute any CPU instruction and reference any memory address. Kernel mode is generally reserved for the most lowest level trusted functions of the operating system. And crashes in kernel mode are catastrophic, so they're going to halt your entire PC. In user mode, the executing code has no ability to directly access hardware or reference memory. Code running in user mode must delegate to system calls to access hardware or memory. And it's due to the protection afforded by this sort of isolation that crashes in user mode are almost always recoverable. Most of the code that runs on your computer runs in user mode. So my Keynote program here, web browsers, etc. And these two modes aren't just labels. They are actually enforced by CPU hardware. If code executing in user mode attempts to do something outside of its privileges, like modifying memory it has no access to, then instead of the entire system crashing, only that particular application will crash. So who uses the kernel? Well, the kernel provides a way for other programs to use the underlying hardware via system calls. And system calls allow user programs to perform actions that require kernel privileges in a safe way. So the kernel is not designed for direct human consumption, like there's no user interface. Instead, the kernel's users are other programs. There are a few hundred system calls, with the exact number varying slightly between different types of architectures. Some architectures have system calls which are either architecture specific or provide different sizes of parameters to the same function. When a system call is executed, the arguments to the call are passed from user space into kernel space. The user process then becomes a kernel process while it's executing that system call. So I've got here a really small C program. Is anyone here familiar with C? How to play around? Yeah, a few, cool. I hadn't really used C since college, so this was like, whoa, when I started playing around with kernel programming. But it's pretty fun. So this small C program, all it does is open a file, copy the contents to standard output, and copy the contents to standard output. And it uses 4 system calls, and I've highlighted them here in orange. So all these system calls involve file I/O. There's open, close, read, and write. Behind the scenes, these system calls are interacting heavily with the hardware. In this case, they might be reading sectors of the hard drive. So system calls provide a really nice layer of abstraction between, from underlying implementation details. So the kernel has 2 main entry points. When a running process or application makes a system call, or responding to a hardware interrupt. So a key being pressed, a network packet arriving, a timer being ticked. And an interrupt is a signal to the processor emitted by hardware or software, indicating that an event needs immediate attention. Remember, the kernel is multi-threaded, so the processor responds by suspending its current activities, saving its state, and executing a function called an interrupt handler to deal with the event. And after the interrupt handler finishes, the processor resumes its normal activity. Most problems can be solved by writing programs in user space. But for those that can't, for example, needing a new piece of hardware to run under Linux, then you'll need to write a kernel module. Loadable kernel modules are just C code, and they can be compiled and added to a running kernel. The kernel uses a modular architecture, which means the core of the kernel can remain small, and all of the modules can be unloaded and loaded as required. And this means that the kernel only takes up as much RAM in memory as it absolutely has to. You'll need a few things installed on your system to be able to write a kernel module. So you'll need to have the Linux kernel source tree, and this is so that you can build your module against appropriate kernel libraries. You will also need to be running the same version of the kernel that you built your module with. You'll need a GCC compiler as well, because again, it's C code, and GCC is a C code compiler. And another program that we use is make, and that's used to call a GCC compiler to build the C code. So I've got up here a really simple Hello World kernel module. And all it does is when it's loaded, it prints Hello World, and when it's unloaded, it prints Goodbye World. And I'm going to break this down. We'll take a look at each section. So at the top, you can see that there are some kernel header files includes, and followed by some license information, which is actually really important because if you specify a license type other than something that's open source, you will taint your kernel, which isn't a good thing because it means you lose the ability to run other open source modules and capabilities. Right down the bottom, you'll see two macros, module init and module exit, and they call our own internal functions hello and goodbye when the module's loaded and unloaded. So our hello world, our hello function here prints hello world, but it actually doesn't print this to the terminal. Instead, it prints this to a special kernel debug log. In this example, we didn't do a whole lot, right? We just printed hello world and goodbye world. But in reality, a module init method might actually do quite a bit of initialization work. So it might do things like allocate memory, register device nodes, initialize hardware, and so on. And conversely, a module exit method must undo all of the work done by init. So it must unregister devices. And free allocated memory and so on. And this is really, really, really important. Exit must undo everything done by init, because if it doesn't clean up properly, then it's going to leave all this memory allocated and it's going to stay around until the system is rebooted. So a few of you raised your hands before to say that you've done some C programming. So how is kernel programming different than writing regular C program? Well, the kernel doesn't have libc, for starters. So it doesn't have the standard C headers and libraries that you'd be used to. Another thing to note is that it doesn't have memory protection. We run this under kernel mode. So this means that we can easily stomp all over other parts of memory and no one's going to stop us. So you have to remember that this kernel module has all of the privileges, so you have to be really careful. It also has a single big namespace. When you program in the kernel, you program in this large namespace that has access to all exported symbols from your kernel module. And these exported functions are known as kernel services. And lastly, remember that the kernel is a multi-threaded environment, which means that all modules must be thread safe. So we build kernel modules, as I mentioned before, using the make program. And the make program reads from a file called a makefile. And this is the make file that we've got here for the Hello World module. And all it does is build our source code against a kernel source tree so that it can reference the library files it needs. So after we have built our kernel module, we need to actually load it into the running kernel. So I'm going to go ahead and do an example of that. Again, please feel free to follow along. We are going to do some exercises after this as well, but so back in home Vagrant handy workshop files, there's a directory called Linux bootcamp. And in workshop kernel code hi, yes, it's very deep in there, we've got our source code. So if I take a look at hi.c, this is the very similar to what I had on the screen before. And in the exercise that you're going to do in a second, or you're going to do right now, we're going to just replace these to-dos with the print statements. So I'm just going to copy those across. Cool. Okay, so in my hello init function, I'm going to print k hello world, and in my exit function, I'm going to print goodbye world. So I'm going to save that file, and now I'm going to run the make command. Actually, before I do that, inside this directory there were two files. There was the hi.c, which is the C code, and there was also the make file. If we just take a quick look at the contents of that make file, again, that's the same as what I had up on the slides, and it's just going to build our kernel, our C code against the kernel source tree. So if I run make, okay, and that finished. If I list the contents of that directory, there's now a whole bunch more stuff since we built our C code. The most important file there is this hi.ko, and ko stands for kernel object. So if we want to now load this kernel module into the running kernel, we use a command called insert module, or insmod, and I'll just make the screen bigger. And we go insert mod hi.ko. Great. So where did our hello world go? So I mentioned before that that wasn't going to print to the terminal. Instead, it was going to print to a special kernel log. And we can check that log by running the dmsg command. dmseg. Wait a second. Okay. So, I don't know why it's not there. Let me take a look at my C code.
Does it need to be mod probed after or
No.
no?
Yeah, it's loaded. So another way to test if it's loaded is to run the lsmod command for list mod. And I can see that at the top here, the hi module, hi kernel module has been loaded, but I would have expected that to hello world to come up in dmessage. If I unload it, Oh, okay. I just didn't see it. Okay. So I hadn't scrolled enough down. So in dmessage, we can see hello world. And I also just removed the module by running rmmod hi to remove it from the running kernel. And that causes a goodbye world message to be printed. Cool. So there's actually a few exercises that I thought that we could just give you a little bit of time to run through. So the first one is learning about what ls mod. The next one was one we just sort of did together then if you didn't have enough time to do that. And then attempt to actually have this high kernel module loaded every time the system is booted. So these exercises are, you can get them off the GitHub. A bit link to that is just bit.ly/workshop-kernel. And they're all numbered. So it's exercises 8, 9, and 10. So I might just give you a few minutes to give that a go. Does anyone have any questions at all? Yeah.
When you earlier when you ran your make command,
Yep.
to build, the build of hour and a half.
Oh yeah.
Right. Did that work because you had already installed the C compiler into the version that you now, the image that we had?
I'm not sure I quite understand.
You said that you have to get a compiler.
Right.
When you're working with
So I think one of the things I did with this Vagrant image before I packaged it up was installed like kernel development tools, and that goes ahead and installs GCC and make.
Okay.
Yeah.
All right, so that the image that we have has it, but if we were to...
If you were to do it yourselves, you would need to install it.
Okay.
Yeah. Yes.
Doesn't seem to print the event message until after you remove the module.
Oh. Yeah.
So print K is line buffer. You put a backslash in after your print message.
Did I? Ah.
The right print
Let's have a look.
K is also line buffer. So if you add backslash in, add it to both the print K.
So I'll add a new line, like this.
So backslash.
That. I never know which one's backslash or forward slash. So, okay, let me get rid of the N. Yeah, okay, so if I load this again.
It needs to be backslash in.
Backslash N, oh.
Like that's the default effort.
Like that. Okay. Oop. Okay, I'll add it here. Let's try again. Cool.
Nice.
Nice one. Awesome. Cool, so this is a first exercise, learn about ls mod. Any other questions? Oh yeah, sure.
Yeah, so normally I've done kernel recompilers before, but I just throw in like a dash J followed by a number.
Oh,
based on
yeah.
the cores that I
Yeah.
have. But I actually don't know, I just kind of do it by habit. I don't know exactly what that does.
It's supposed to speed it up, absolutely. Yeah, so when you compile, I was saying before that compiling takes like an hour and a half. You can actually put a command in to specify the number of processors or something to use, and it's supposed to speed it up. So I believe that it does, but still nothing too quick. I don't know, Jesse was saying yours only took 30 minutes, right?
Yeah, you can define the number of threads you want to use.
Yeah.
But I mean, I use a lot because I compile kernels a lot, but also then my computer sounds like it's going to explode. So.
Yeah, and I just
There's
have like a
trade-off.
Mac Air, so it doesn't have a whole lot of grunt, so it takes a really long time. But that's a good thing to do for sure.
Oh, I use i3. It's the best window manager. It's a tiling window manager. Like some people like Xmonad, my coworkers. But then I converted them all to i3. So if you want to be cool like us. I'm pretty much the worst about it too. I'm like, I started that trend, so. Yeah. Their code is on GitHub too. I like really wanted to add, because I got this like new Dell like touch screen. I want to add like touch gestures for it, for like swiping. That'll be cool. But yeah, there's no time for that. Okay, so some other stuff that we can go into that's like kind of cool. There's a bunch of different commands for like debugging different things on Linux. One of the most common referred to, I guess, is strace, which traces syscalls. I use this like all the time, mostly because, well, I use it one to trace processes that appear frozen to make sure it's still doing something. And then also, since I run everything on my host in Docker containers, which is really weird, when I was packaging all these like apps into various different images, it's not exactly easy to start from nothing and get the package to work correctly, because usually there's a bunch of deps that like you don't realize are deps, and they're not actually considered a dependency in the Debian packager, which is really weird. So if you trace the process, it will be like no such file or directory, and then you have to like download that .so file that it's looking for. Yeah, trace is cool, so we can show that. Just a very simple one would be trace ls. You can show it like writing to the TTY output, and like it's, you know, looking in different files, statting, opening. It's pretty cool. I mean, it's like pretty gross output, but you know. You can also like trace on a process itself. Wow, this is not all the way down. Cool. Let's just grab one. Let's cron. GNOME. Trace HP. Oops. Oops. Yeah, so that's like whatever that process is doing. It's pretty cool. Not that great. It's really gross output, as you can tell, but like if you grep it for like whatever you're looking for, it's a lot easier. In this, in the repo on GitHub with all the other stuff, there's an advanced portion of this. Hang on. Where's my mouse? Just kidding. So there's like this advanced file, and I put this link to my coworker's blog post. He works on my team, and this is like something for you to do at home, but I just wanted to stress that it's really cool. He goes over like different things about namespaces in the kernel, and there's like some C things that you can run, and it goes over just like basic things like networking namespaces, user namespaces, all the things that really are like a part of Docker itself, because we consume so many parts of the kernel. There's a lot of syscalls in the code. So he like abstracted a lot of that away and made a very basic tutorial that he never wrote the part 2 of, and I keep bothering him about. But part 1 is really cool, and I would highly suggest you take a look at it because it's like awesome. So yeah, there's that. And let me bring this back over. My mouse keeps like getting caught in the VirtualBox. Okay. Jeez. Okay, this is just the worst. Sorry, I usually don't have this much struggles with life. There we go. Okay. It's really weird for me to use Ubuntu too. I'm like a huge Debian fan because it's called, I mean, their latest release was called Jessie. So, I mean, there's that. Okay, so, wow. Moving back to what I was talking about. Sisctl is like a command line tool where you can change the contents of the files in procsys, which is kind of what Georgi showed before, but this way you can do it through the command line. You don't have to like echo into a file. We actually use this a lot in the Docker codebase for things like turning on IPv4 forwarding and various different things that we need to make sure we can do everything. We do things very closely to the kernel, but yeah, we don't like shell out to Sisctl though. I mean, but we change contents of proc. Just to show an example of this, we can view all the system params with. I swear to God, it's like not working. Okay. Cool. Sisctl-a. And I'm gonna have to sudo that. I know it. Cool. So like that's like basically everything how it's configured. You can let me just because I'm lazy. Cool. I don't want to have to sudo everything. So then like you could technically grep that for what you want. It seems like super basic. Sorry. And you can even change like, if we say edit a file, there's multiple ways to change Sisctl. So one of them would be editing the Sisctl config. Wow. Which, I mean, this basically is so that the state is saved over time. So you could edit that file, or you can just run a command, which would be, okay, so if we look at the command for, oh my God, going to kill my computer today. Sisctl, file max. So like our, so that's what it is before. We can change it just by doing this. Dash W. Equals like whatever we want. And now it's a different value. So that's cool. Like various things you would want to change in there. I really am only familiar with the networking ones. Stuff like IPv forwarding, like Docker turns it on, but when I want to do stuff with Tor, I turn it off. It's just, yeah, various different things. Let's see, that was kind of all that I had. If you're like interested in more like in terms of like C groups or namespaces or anything like that, you can like ask me questions after. But I would highly suggest looking at my coworker's blog post because it's really cool and he's a good writer. So yeah.
So that's pretty much all we have for you today. But I wanted to kind of go over like a few like next steps from here if you're interested in continuing learning about Linux, because there's quite a lot of good resources out there. So one of them is this edX course. And it's an 8-week course, which is an intro to Linux. Some of it is pretty basic, but it does go over a lot of like core things around Linux, like permissions and the file system, etc. And that could be quite helpful. Another thing to do really is to try and install Linux native. So we've got an install here via VirtualBox, but it's really fun to try and install it yourself. And Jesse wrote a really cool blog post called Linux or Death, aka How to Install Linux on a Mac. And I have gone through this blog post myself and successfully installed Linux on my Mac Air. It's really good, and in it she even configures and builds a kernel and stuff. It's a super awesome blog post, so I highly recommend giving that a go. And lastly, if that kernel programming stuff sounds of interest to you, there's this really cool thing called the Utoptooler Challenge. I think that's how you say it. But basically, they copied the idea from the Matasano Crypto Challenge, which you might have heard of, which was kind of really popular. And the general idea is you sign up and you get sent like a task to do via email, and you have to do it and like send the output back, and you progress through like 20 different levels. And it's really fun, and the whole point of it is so that you learn more about the Linux kernel and even eventually like submit a patch to the mainline Linux kernel, which is super badass. So if that sounds like something you're interested in, I recommend giving that a go. Tammy mentioned before Vim Adventures. If you want to get better at Vim, that's a really fun game to play as well. I have listed all of those links on the OSCON website for the bootcamp here. And again, all the exercises we went through are written up in great detail on the GitHub page. So thank you very much, everyone, for coming today. We had a really fun time. You've been great. Thank you.